Gonna start recording.
Perfect. All right, everyone, welcome to, I guess this is our third meeting of the quarter. I know it's starting into midterm season, so thanks for showing up. Today I'm going to be talking about software-defined radios, why they're cool, how they work, and what you can do with them. That makes sense. Yeah, so I'm going to talk about what SDRs are, what makes them different from normal radios, some of the architecture, some of the hardware you can buy, and some you can afford, and probably some that you can't, and the software you actually use to control them and use them. Next slide. All right, so what is SDR and why is it cool? Basically, the idea is we want to convert RF to digital as quickly as possible. So this allows us to do RF demodulation, signal processing, and filtering, all the stuff you normally do by designing a circuit or designing RF passcan or whatever RF device you're going to do. It allows you to do all that in software and apply software development workflows to it. It's a lot faster. You can push updates to radios and reprogram what they do. Yeah, so we're trying to do as much as we can in software. Next page. Yeah, so it's another very interesting part about software-defined radios is you can do some really cool signal processing math that is just impossible to do in hardware. I think I'll talk about it a little later in the presentation. There's this cool thing, cool optimal filter for getting the perfect maximum performance out of like a PSK link and minimizing the amount of intersymbol interference. And you can approximate it in electronics, but you don't get the performance that you can out of just applying the math in software. Next. So a couple things you can do. You can receive normal signals, just demodulate them like your normal handheld would do. Listen to broadcast radio. You can do listen to police and fire. Some of them run trunk systems. So in the Bay Area, where I'm from, there's a massive P25 digital trunk system. And the only cheap way to listen to it, if you are interested, is software-defined radios. Hardware radios that can actually demodulate them range from like $600, $700 and up. Or you can do it with a $30 dongle, software-defined radio, which is pretty cool. You can track aircraft with ADS-B. All aircraft are required to transmit out their positions, so you can just listen for that. You can track weather balloons. So this is me last winter break, headed out to the ends of Borrego Desert with a software-defined radio and my laptop, and tracked down some weather balloons out in the desert, which was pretty cool. You can decode GPS satellites. So they're just transmitting what they do would go into a normal hardware radio that does all the demodulation there. But if you do it in software, you can, for example, do stuff like get around ITAR regulations, which I'm sure is you don't want to be doing, but you could build a software-defined GPS decoder that can go faster than
great accuracy too.
Oh, with better accuracy than they allow. You can go at altitudes that are normally restricted. You can go at velocities that are normally restricted. Don't do it because they don't want you to build a ballistic missile with it. That's why those restrictions exist. Good. You can sniff GSM signals. So this is cellular stuff. You can pipe that into some software and start, listening to carrier broadcast messages that controls your phones. I know some people were researching the recent emergency broadcast alert we just had. They discovered some vulnerabilities even in the most recent version of like 4G and 5G systems, where if an attacker wanted to, they could just send out fake emergency alerts to people. People sent those signals and figured out, reverse engineered, and figured out what you need to do to attack that. That's good. Oh, another fun thing, you can decode oxide. It's a really old pager standard. Unencrypted, you would think it shouldn't be used for anything, right? Wrong. It is used to transmit sensitive health data inside of hospitals. So if you're near a hospital, again, I don't recommend sniffing data. It's data you really don't want to touch. Trust me, you do not want to be getting involved with that. But it's a real problem, and the hospital should be fixing that, but they don't. You can find them, go around 900 megahertz, and you'll hear it. All right, next slide. All right, so this is the most basic way you can make an SDR. The most like what you might first think. Let's just take an antenna, put it into an amplifier. The signals coming in from antennas are like microvolt level or lower. They're really low power. You can work out the math with dBm to convert that to power. Use 50 ohms as your resistance. It's really, really small voltages. So we amplify that, put it into a really expensive ADC. We sample really, really, really fast. And we can take that and pipe it into a Fourier transform, finite Fourier transform, right? We have a discretely sampled data, and then you can pull information from that. But that runs into a couple problems really fast. First off, you can only see from what we call DC or baseband, 0 hertz, all the way up to half of what you can sample on here because of the Nyquist limit, right? You can only see up to, you have to be sampling at double the rate you want to see. So you have to start to go higher and higher frequencies. You have to get a really, really, really expensive ADC. They get exponentially more expensive as you try to sample faster. And you also run into issues where you start sampling faster, you have less time to actually collect like electrons. So you're going to start getting more noise, and you're going to start getting less sensitivity and less bit depth. Essentially, you get less resolution. So to solve that, next slide, you do a thing called mixing, which is where we take this nonlinear like Ferris device and mix in an oscillator signal. So we'd still have the antenna amplifying the input. Then we now take that into a mixer. We have to put filters on it because it's nonlinear. So we filter out what we want our input signal, where we're trying to proceed from, and where we're trying to mix it down to. We take our local oscillator, say we're trying to receive a signal 1 gigahertz, right? So let's pick, maybe our ADC has a bandwidth of, 400 megahertz, sampling at 400 megahertz or 400 megasamples per second. We can see 200 megahertz spectrum, like DC to that, right? So if we mix a 900 megahertz signal into the oscillator, it'll create products. It'll move the input frequency out on the output side to 100 megahertz and 1.9 gigahertz, and keep subsequent products from that, which is why we filter it. It also will go into the negative. You think negative frequency, what does that mean? It's just the same as positive, but flipped around. So we'll go, what's that, -800 megahertz. So you'll get the exact same signal coming out at 800 megahertz, flipped over, 900 megahertz, 1 gigahertz, and it starts creating a lot of harmonics, which is why we add filters. But we then pipe that in, and it lets us, tune our LO anywhere we want, and we can see a little chunk of the spectrum based on how expensive of an ADC we buy. Next slide. So that still has problems. As I was saying, it creates the sum and difference, and it does some other weird stuff. So there's a really, really cool architecture. This is what pretty much every modern SDR uses. It's called IQ, or in-phase and quadrature demodulation. So this solves a couple problems at once. First off, we have two ADCs. Two ADCs that do half the bandwidth is a lot cheaper than buying one ADC. That's more of the bandwidth, because as you try to sample faster, your price goes up exponentially. Another thing is, since we're sampling twice, we easily get more bandwidth, and also we're going to get rid of the imaging problem where we can't tell. In the last one, right, we're saying it adds and subtracts. What if there's a similar signal at 700 or 800 megahertz coming in, gets added to 900, we go to -100, and it comes back out on top of our 1 gigahertz signal, right? So they both come out at 100 megahertz, and we're sampling the same, or two different signals in the same spot, right? So we call that an image. IQ gets rid of that. I'm going to explain very quickly on the whiteboard. I don't know how many of you all have taken, I think, circuits tutors that I introduced phasers. So let's see. Let me grab. pen from my bag and try to quickly explain why IQ is really special. So we have our LNN, right? Connected to some antenna, signal comes in, it's going to get mixed twice. This is our in-phase channel, mixed again on our Q channel. So these are basically, we can think of them as sine and cosine frequency locked together. They're 90 degrees out of phase. That's what we call it quadrature. This is typed in here, right? So on the input, we'll represent our signal as a vector in the complex plane, right? So this is going to be has some magnitude, some degree. This is going to be basically how strong our signal is and what phases our signal. The exact number doesn't really matter, or the exact degree. But this is a very convenient way to represent a sine wave, right? This tells us everything we know, how big is it, and what's its phase shift. So sine we'll just represent as a straight vertical line, and cosine will be straight to the right, they're whatever 1 unit. So we take our signal, it gets mixed, and when it gets mixed, it comes back out, add and subtract the frequency, right? So when you go here, you will see this comes back out in phase if it's above, right? So this will be represented with a, what do you call it? A 0 degree phase shift. And so we'll see the same signal come in like this, and on quadrature, 90 degrees or 90 degrees behind it. That's if we're above frequency, right? That'll come out 90 degrees behind the exact same signal because we're mixing them with 90 degrees apart. So in the computer, we'll take these samples and see, oh, it's 90 degrees apart. I know that means it's above the frequency or below the frequency when we do the Fourier transform. We can also see as the frequency of this signal isn't locked to the frequency of these signals, we'll see an oscillation between the two, right? As it goes in and out of phase between one and the other, right? So we have two very close frequencies in the waves. So we can use that and the phase difference of when they come in across the two to basically work out all of the original information from the signal. So then, say instead of above, we come for below. If this frequency is a little bit lower, it gets mixed, and this actually comes out on the other side, and we'll see one channel, the I channel, instead lagging the Q channel. The math behind it, exactly why it happens, is really complicated. If you think about it long enough and think about how mixers are working with their diodes, it starts to make sense. But basically, from our I and Q data, we can work out everything about the original signal for free, and we don't get the imaging problem we had in the just directly down converting with the mixer, which is really cool. So it solves both of our problems at once. This is basically what all modern SDRs do. Next slide. So that's enough math. Let's talk about things you can buy and play with. So this is, as I was talking about, $30 dongle. You can buy it on Amazon. They're super cool. I would highly recommend picking one up. This is actually what got me into radio and RF before even amateur radio. Next bit. So yeah, they provide 2.4 megahertz of bandwidth, which means you can see at once 2.4 megahertz of the spectrum. You can move it anywhere you want within 0.5, so 500 kilohertz to 1.76 gigahertz. So you can see a considerable amount of the spectrum, not Wi-Fi, not some other stuff. Still pretty cool. Yeah, $30 on Amazon. Next thing. Oh, and then important, these are receive only. Some SDRs transmit. It's actually the exact same process, except instead of typing these into an analog to digital converter, we synthesize the wave we want, do all the modulation software, come up with what I and Q channels would correspond to that, and then just play it through a digital to analog converter, like what we do to play audio, but at a much faster sample rate, right? We need to be at twice our bandwidth for mega samples per second compared to what's audio, like 44 kilohertz. samples per second or something. Way faster, and then just mix it this way. So mixers actually they same hardware, they work both ways. And then instead of a receive amplifier, we'd have a power amplifier going out. So in a couple slides, we'll get to some transmit capable SDRs. So yeah, here's the HackRF one. A lot more expensive. Gives you 10 megs of bandwidth and 1 megahertz to 6 gigahertz. Yeah, $350 are not cheap. If you want to play around with one, the club has one, we can lend out to people. And they're half duplex, which means you can transmit or receive, not both. Which very similar to how a lot of other radios are, right? You're transmitting, you can't receive simultaneously, but it's some other SDRs don't have that limitation. Next slide. Here's the Pluto. This one's actually this SDR is super cool. If you're more interested in SDR, more deep dive, way more than the overview that I gave here, you can take EE504. They operate every spring. In that class, you'll use this device to go through some labs, receiving signals, decoding signals. This is what they use in class. It gives you around 20 megahertz of bandwidth. You can't actually get the whole bandwidth over the USB, but it has a built-in FPGA if you write and I don't FPGA and ARM processor running Linux inside. So if you write some code that needs the full 20 megahertz of bandwidth to do something with the spectrum, you can run it internally and pipe the data out over here instead of just getting the IQ data over that, doing the demod on your laptop. It's really cool. They are what, $230 from analog devices, and they're full duplex, so they have separate transmit and receive antennas. And you can transmit and receive these simultaneously. They have a pretty cool feature. A lot of SDRs, you really don't want to do this. But this one, you can actually take a coax jumper, connect the transmit right into the receive, where on a radio that would usually destroy a receiver if you connect to the transmitter into it. But these are designed to be able to take it, and you can actually use it to do transmit and receive simultaneous tests on frequencies you don't have a license for if you need, right? You're trying to decode from a spacecraft and you don't have the license to be transmitting in that band, but you want to write a ground station software. You can write a fake spacecraft that transmits fake data and types it into your thing for testing, or whatever else you want to do. But yeah, as I said, they have a user programmable FPGA inside to lift some of the signal processing work, filtering work, whatever you want to do off of your CPU. That's one thing. SDRs, the math behind them is pretty complicated, pretty intense. So they consume a lot of CPU power. They'll kill your battery off really fast. Next slide. So yeah, here's a Lime SDR Mini, very similar to the Pluto, in which it's full duplex, both transmit and receive. Sorry, slide. I think it's the arrow. Yeah. Also has a user programmable FPGA, just a little bit higher specs. And yeah, a little cheaper, but they're hard to get a hold of because you have to get them from ground supply, which is whenever Lime decides to manufacture some. So they're a pain to get your hands on, but they give you a lot more bandwidth, and they actually have USB 3.0, unlike the Pluto, which is 2.0. So you can actually
process all that.
You can push 60 megahertz bandwidth through 3.0. 2.0 you cannot. They're limited to like just over 10 megahertz, I think, of bandwidth you can push over a 2.0 connection. These are pretty cool. I really want to get one whenever the back in stock. And then probably one that you cannot afford, the next one, the USRP X4400. These things are awesome. These are one of the newer models from USRP. They go, 3.8 gigahertz total of instantaneous bandwidth. That's how much of the spectrum you can see at once. They're 8x8 MIMO, which means they can transmit 8 separate streams simultaneously and receive 8 separate streams simultaneously. They have a humongous FPGA inside, 8 gigs of FPGA capture buffer, so you can capture, 3.8 gigahertz of bandwidth into memory. You can dump that into memory for, a couple milliseconds of RF, and then process that later if it's that intensive or whatever your application is. And to accomplish this, they have 200 gigabit fiber connections. Usually this would be going to some external captive server filled with like NVMe SSDs in RAID 0 or something to keep up with it. Even that probably doesn't keep up with 320 gigahertz of bandwidth. But these are super cool. I think they start at like, yeah, 20, 25 or $26,000 if you want to buy one. But
who needs that? What's that used for?
I mean, you can do like really high bandwidth wireless communications stuff. You can do like signal propagation analysis where you need to way oversample. One of my good friends did his master's thesis here in X-band radio propagation. So he was using a similar lower spec USRP. Actually, Dr. Derrickson has a pile of not these much cheaper ones. Still multi-$1,000 SDRs if you want to borrow them for a project. And he was oversampling like quite a lot this 10 gigahertz beacon, and then doing like time correlation. So it was transmitting pseudo random data from one side, and then transmitting it over the ocean from, I think it was from a boat to the shore on the dock where he was receiving it, and then correlating the pseudo random data on the shore side to try to measure the multipath, which is where you get your 10 gigahertz signal going straight to the receiver, and then you get a much weaker signal where it went up and then bent with atmospheric water and atmosphere, or like just different atmospheric moisture layers on the top of the ocean. It forms like channels where it'll bend and come in. You can measure like really close together, delayed signal coming in multiple times. So he was trying to measure that. You need to way oversample what your data rate is, way more than what your actual bandwidth of the signal you're sending. So that's one potential use of this. And if you have the money and you're developing 5G ultra wideband or some stuff like that. I mean, what's it, 802.11b or something? Forget which the Y gig standard is. It's like multiple gigahertz wide. It's a multi-gigahertz bandwidth. So if you kind of develop something like that, they do most of that processing on like RF system on a chip stuff where all the stuff is really hard to build. You build it once and you buy the chip and it does it. But if you're trying to develop that, you need expensive hardware like this. Next slide. Oh, and then something different. The Kraken, this is actually a lot cheaper. They're a little hard to find right now. They're out of stock again. They keep coming in and out of stock. They're $500 on Crowd Supply. They're really cool. They're basically take 5 RTL SDRs, the first little dongles I was talking about, stick them in a case with all on one board, one USB hub, and then they have a not quite precision, but a noise generator that gets injected. So it combines the receive signal from each of the 5 antennas with some noise that's generating and amplifying internally, adds them together into the input of each of the receive-only SDRs. And then in software, you can correlate the noise, that noise, background noise source that's being injected with all of them to phase sync everything. And then by phase syncing the signal, you can determine the exact phase difference when it hits all 5 antennas and tell which direction, like which exactly like a polar plot of power distribution. Like, oh, most of the power came from here. They've actually done some cool experiments where if you have like a transmitter, your receiver, and then a hill behind you, you'll see a big lobe towards the transmitter and then a small lobe reflection off the hill. They've done cool like backscatter radar, just using radio station signals to, you can measure where they're bouncing back off from, the smaller bounce backs, and measure the environment surrounding you.
I think these are super duper accurate to like the traces on them have like compensation for length and bends and stuff.
Yeah, the accuracy of this is wild. Yeah. They had to deal with I believe it was ITAR as well. ITAR has weird restrictions on direction finding, RF direction finding hardware that has more precision, like 3 degrees or something. And this goes more than that. So they had a little small period of time where they were having issues selling it, but we can buy it again. They also have cool functionality where you can pair it with a GPS receiver, put these antennas on your car, drive around, and it'll make a heat map of where the signal is probably coming from. Or if you have a couple of them connected over the network and you tell the software exactly where all of them are, it'll triangulate the signal and build a heat map from that as well, which is really, really cool. But I think next we have, some of the software. So this is SDR chart for Windows. You know, you plug your $30 dongle in and you just see signals, which is really cool. You just click around and tune to them. If you want to try this out, we have some, I think, couple spare in the shack. We have some SDRs if you're interested in something like this. This is what I'd recommend. This is usually what I do to find an interesting signal. Next slide. And then, GQRX, this is what I really like. It's compatible with Windows or Linux, and I believe Windows as well. SDR Sharp does not work on Linux, but this does. I usually use this. Has a little less features, but it's cleaner and faster. You know, it works.
Also, the new SDR Sharp menu is so confusing.
Yeah, SDR Sharp does a lot, but GQRX is simpler and faster. I think GQRX also works with Windows, but on Linux, definitely this is what I use. And then next slide. Then there's GNU Radio, of course. The big, so GNU Radio is one big set of signal processing tools and everything, mostly all written in C, C++, some of it optimized, platform specific optimized for certain CPUs written in assembly, which is really cool. So you'll run, when you install it, it runs this profiler on your computer that takes like 15 minutes. It'll determine which implementation of the algorithms, of each algorithm runs fastest on your computer to optimize it. And then all that's wrapped behind Python. And then there's this really cool GUI plugin where you can drag and drop signal processing blocks and build a flow to demodulate and modulate signals into various SDRs. So it wraps the underlying drivers away from you. You don't have to deal with actually talking to the SDR. It does that for you, and then you just deal with the signal processing map, which is really cool. Sometimes it's really finicky and hard to get working. So usually what I do, if there's a signal of interest, I try to find it on GQRX, find it, see what its bandwidth is, where is it coming from, and then go into GNU Radio and see if I can start demodulating and pulling some stuff out of it. This flow I have here, it's really big and actually really hard to read, but it's from the ISE3 reboot project, which was actually, was this like 2014, 2015 or something? There was a small team of engineers who were able to, it's like 3 or 4 people, rather tiny for what they did. They were able to take a USRP, one of the older models from around at that time. It was given to them by a company, NS, that designs those software or those software-defined radios. And they designed this satellite ground station software that was compatible with all the old NASA docs they could find from the ISE3 mission, which was late 60s, early 70s or something. It had escaped Earth and it was in a solar orbit and it was going to do a flyby of Earth again. So they actually took their SDRs down to Arecibo, connected them up with this massive traveling wave tube, like multi-kilowatt amplifier that this ham in Germany built for them. They shipped it there, whole RF front end of filters and amplifiers to get it to that, hook the output right into the Arecibo dish. And they were actually able to wake up the satellite, download telemetry back off it. So they were able to turn it back on, get telemetry from the mission from right at the end of its life, the original mission life that NASA didn't have. The goal was to wake up the propulsion system and have it do a capture burn and then go into Earth orbit again. But they weren't able to do that. They were able to wake it up, but now it's gone.
So that in itself is pretty impressive.
Oh yeah, it's super impressive that they were just with SDRs were able to wake up this 40-year-old satellite.
And so they were able to just get docs online to do that?
They had to contact some people at NASA, and they had a little bit of help with from some of the old engineers who had worked on that project way long before. And they built, I mean, as I was saying, they did build a big satellite in SDR, and they were testing it for months before the satellite flyby. It was, yeah, super cool project. I have a link to a talk one of them gave at a software defined radio conference if you're interested, about the project and what it entailed. It's a really cool talk that I can take a look. Yeah, the kind of stuff you can do with SDR is really cool. I think that's it. Yeah, if you have questions, email me or on Discord. I'm happy to help you with any SDR or anything you're interested in. I think SDRs are cool, so if I can make time, I'll help you with it. Does anyone have any questions about, SDRs, SDR systems? What I was going to add more slides about SDR system design, but I school midterms.
I'm really interested in the ADSB decoding.
Oh yeah.
Have you done anything in that area?
I haven't, but the club does. We have an ADSB decoder in the rack.
Oh, cool.
In the shack set up, just sending data to FlightAware.
Oh, cool. Okay.
I know I can get you in touch with some people in the club.
That'd be cool. Yeah.
Or some people who've since graduated. Or if you just want to come and poke around with the shack board, you're more than welcome to.
Okay, cool. Yeah.
It's fairly simple. I know it's a piece of software, and the ADSB is pretty low bandwidth, so you can just take an SDR and a proper antenna, and then if you have a filter and an amplifier for that frequency, you'll get a lot more range out of it as well. Okay. Cool. All right, I think that's it. If anyone wants to check out SDR hardware, by the shack, we have some there.
This is my first meeting, so I don't know anything about the shack. What is that?
Shack's our club room. It's
Okay.
right outside, and then right back there.
Okay, cool.
In the footer.
Cool. Do you guys have meetings like in there, or
No,
do I like contact someone for like?
They're always in here.
Okay.
We have events, usually HF Fridays in there. Every Friday evening, we usually meet up, do HF operation or work on homework, or just hang out. It's kind of office hours. Otherwise, basically any time during whenever this room's open, you can access it just by going through here. The gates out there is locked, so you can access it by going through this room and then knocking on the window. There's usually people in there.
Cool.
Yeah.
I've seen some like open source implementations of like clones, like the Lime SDR, and like on GitHub, and then like some even like
Of the hardware, or
the hardware to like constructed and like posted on like AliExpress and stuff.
Okay.
Like, what do you think of those? That's cheaper too.
I've seen that for the hacker app as well. I don't know. I mean, I've never tried it. One of my good friends from high school bought one of those clone hacker apps for like $40 or $50. I don't know how much success he ever had with it. Interesting to try.
Yeah.
All right.
Another thing, does the temperature of like the SDR itself affect any of the components, like the noise or anything, like within the unit?
Yes, but not that much. So we talked about this in the class in 504, where SDR noise. There's three main sources. There's thermal noise, shot noise, and 1/F noise. Okay. So thermal noise, of course, the hotter it gets, the more noisy, the more noisy it gets. I forget the exact formula, but every resistor puts out noise, the hotter you get it. So if you just measure across a 50 ohm resistor, you'll see, like, you just coax up solder to a 50 ohm resistor, put that into a radio and start amplifying it. The noise level you come back, you'll see back out of it is directly related to the temperature of the resistor. So you'll get like, it's like minus 120, or once you start getting it warmer, it goes like minus 110, maybe minus 100 dBm when it's really hot, but that's still almost. minus 110 dBm is like it's comparable to a really weak signal to be getting. So that's around what your background is.
And another thing, when I've been using like the SDRs, sometimes encounter like a noise spike on like the center of the spectrum.
Oh, right in the middle.
Yeah.
So that comes from you have to do DC elimination.
Okay.
I think called that's baseband, right? So within the IQ modulation, how it's doing it, middle because of how it reconstructs it, the middle frequency that you're tuned to, your LO frequency, is getting mixed down to DC. So you're losing a tiny bit of like resonance, and it's so you see a little spike. It's why it does that. I don't know. This comes somewhere. Something comes from the math of doing the Fourier transform, where you get as your frequency gets closer to zero and your sample rate is finite, you start seeing higher colors.
Then could that just be like that part be suspended in software?
Yeah. They're in the driver settings or somewhere in the software. They have a thing called like DC elimination. I think it's like a checkbox in GPRX or SDR shop and like the SDR stuff.
I've never seen it in SDR shop. I should check that out.
Yeah, I mean it's not that important. Like tune off by a couple kilohertz of what you're going to receive.
Ryan, do you want to bring up the GOES project potentially?
Go ahead, Matthew.
You want to bring up the GOES project potentially with the dish we have?
GOES.
Yeah, so another SDR related project around the club. We've been trying to receive or set up a GOES ground station for quite a while. Just received their, what do they call it? HRIT, high rate image transmissions off the satellite. So it's about a 2.1-ish megahertz wide signal, around 1.7 gigahertz coming off these geostationary weather satellites. It's really cool. You can get full like hemispheric disk images of the Earth in real time off the satellites. But we've had problems with antennas and amplifiers and stuff. But if you're interested in and want to take charge, we have some hardware to play with it. If you want to get that going. Right. Yeah, I don't have time. I'm a full-time student. That's probably most of you are. But
Which satellite did you say that's?
GOES. GOES. GOES 16. 18. I forget. There's a couple. There's two of them that are currently active, and I think one that's in reserve. They're geostationary weather satellites. One of them covers the West Coast, one of them covers the East Coast. Or that's what's centered on the disk. And then there's actually a much harder project at lower signal power and more annoying to demodulate polarization. So there's this other thing called the GRB, the GOES rebroadcast. That's the full data set. It's much wider bandwidth. You need a much more expensive SDR, and it uses what's called MIMO, multi-input, multi-output. So it's two spatial streams. There's one coming down that's left-hand polarized. So they're circularly polarized rather than linear, like a lot of the other stuff. So the HRIT is linearly polarized, which makes it easy to do. Otherwise, you have to build circularly polarized 1.7 gigahertz feeds for both left and right circular polarization. Helical feeds. Both polarizations feed them into two separate SDRs and combine the channels. You need to receive both to do it because it transmits. Basically splits the data in half, so it can fit double the amount of data or double the amount of bandwidth at the same amount of frequency.
It's just exactly the frequency.
Yep.
That's crazy.
Yeah, it's a lot more. You need a lot bigger dish. It's a lot lower power and a lot wider bandwidth. It's not really meant for people to be picking up.
It's for like meteorologist stations.
Yeah, kind of. I mean, that's kind of what GRB or HRIT is for like amateur and commercial people, like stations to pick up and take that data. It's more compressed, not as high-res data. And there's some stuff that's filtered out. like they'll send commands up to the satellite, say, oh, zoom in on this, send, the high res data from this portion of the US. Like if there's a hurricane, they'll zoom into one area and send that with it as well, the high res data for there. The GRB data, there's only a couple ground stations around the US that pick it up, and then most of them, all gets forwarded to different headquarters.
Go to the NOAA website and find it.
Yeah, you can find, I think it's through NASA's website, you can find like 12 or 24-hour-old imagery off the satellites.
Oh, and yeah, you can
Those
keep
sensors.
receiving them and make time lapses.
I really want to do that. But we
Yeah, and I've also seen like multiple dishes and SDRs pointed at satellites spaced out, and like you unwrap the images and stitch them together, so you get like
Oh, that'd be
big
cool. Yeah, because
map, which is pretty neat. Yeah.
the two main ones, it's like those what's 15 or I don't remember. They're at different
Yeah, so
different positions.
we see both of them unwrapped the circular like rectangular map and then stitch them together. It's pretty cool. Yeah.
And then I think also goes, which I forget which one it's called, the goes West Coast one. Also is getting data. I believe it's straight satellite to satellite from a similar Japanese.
Oh, the Himawari, I think.
Yeah,
right?
Himawari. And it also rebroadcasts that in also low res data. One of its data streams coming down is, so you can get even more. Another
like
another
relayed over, so more coverage of the earth.
Yep.
Yeah.
really cool project. I want to do it. I want to do it.
And I think like the V3s can pick them up pretty good, right?
Yeah,
it's like
so if anyone wants to do it, we have a dish. I built a new feed form. I retuned the feed from 2.4 gigahertz to 1.7 gigahertz. I think I tested it on an LNA, but you might want to redo that and make sure the antenna is tuned properly. And I have, or on a VNA, and then I have the LNA properly to do it, all the receive amplification. It's mounted it inside the way down to on the antenna. So with bias powered, one cable coming out of the antenna, so put it in the right spot, plug it in, the SDRs, the RTL dongles provide bias power, DC, it injects DC off the coax. And then all that really needs to be set up to the software. But
again, there's automatic switch for that too.
yeah, I mean, if someone wants to do it, it should be hopefully a weekend project. Most of the hardware is sitting in the shack.
Yeah, great.
Okay. No more questions? Any more questions?
Does BIOS-D induce noise to the coax? How does it transmit it?
It's at DC.
Okay.
So basically you take your coax looks kind of like this, right? So you have, your antenna here. This outer shield is your jacket. This is just like a normal dipole. You have two lambda over 4 pieces for a total of lambda over 2, halfway dipole. Great. So what you do is you just take, say we have an amplifier up here. So first I'll show how the DC injection and DC block works. So you have just like a capacitor blocking DC, right? Any high frequency subs still pass. Then you just connect this up to the proper way up to some plus voltage that you're injecting along it, and then starts ground. Just outside so you've got it anyways. Same thing around on this side. You have your amplifier, and then you would similarly have a DC block capacitor on the RF, and then just pull
For the circuitry.
Yeah, so you filter out the RF. You have some like low pass filter here, and you have a high pass filter here. So you cut the DC into the amplifier, and then just this way. So if you do it right, it really does matter. Your LNA, actually, your LNA noise temperature is going to add noise to your system, not related. Yeah, okay. Again, something you talk about in 504, you really, well, the main thing that sets the noise of your system is the first stage receive amplifier. Everything beyond that doesn't really matter. Once from the first stage, any noise from this amplifier, but any noise that comes in this way, from the antenna is gonna just get successively amplified. But if you amplify it really well with a low noise amp, nice amplifier, you can keep it cool. Again, as I was saying, the three sources of noise, one over at thermal and shot. So keep it cool. You limit your shot noise with the different semiconductor chemistries, and you know, maybe even liquid nitrogen or actively cool this LNA. You can get the noise temperature down really low, and then once you amplify it beyond that, your signal has already been amplified above. So yeah, this is mainly what sets the performance of your system in the first stage. It's really dangerous. Not really DC. Once you're down, once you're past this amplifier, the signal has been elevated mostly above the noise, assuming you're receiving noise.
Another question.
Yes, of course.
How does the auto software gain work?
Couple ways. There are in a lot of SDRs, like in an RTL, there are LNAs on the receive side. So it will just, if it's over like flipping, blowing that the ADC out, it'll just turn the gain down. For the software, just straight software, it just is scaling the IQ data. From that, you're losing, not doing it in hardware, but doing like auto HEC in software, you're losing dynamic range, right? Because you only get the dynamic range of however many bits you're using to sample up the load.
And the amplifier noise.
Yeah, well, yeah, you're getting more noise because your resolution, I forget what they call it. Yeah, quantization noise. So you get more quantization noise that you're amplifying in software by then with math, just turning it on. So it's better to do that in hardware before you quantize your signal with the digital. Okay. No more questions from Zoom? Matthew, anyone else? I can't see who's on.
Matthew.
Yeah, we're recording the meeting.
Thank you so much.
Of course. Anyone who's interested, feel free to check out the shack afterwards. If you want to see some hardware in action or play with it yourself, check it out. Take it home for a week if you want.
Oh, Don is here. Good morning, Matthew.
I love where we're still recording too.
Are we?
Yeah,
Oh.
yeah, I see the record button.
We love to see it.